Вот Кихтенко.
Нет, мне не получилось попасть к нему, я хотел. Я хотел либо на квантовую связь, потому что я занимался, у меня дипломная работа была связана с исследованием квантовых шумов на алгоритме квантовой телепортации. То есть я думал Кихтенко, либо в квантовую связь, вот это туда. Два ответа, которые у нас есть. Но тогда не получилось. Я пытался, но сказали, что мест нет. Ну и я, получается, попал в НСТ. Сейчас занимаюсь совсем другими вещами. Решил попробовать.
Всем здравствуйте, кто собрался. Не слышу никаких
Здравствуйте.
жизней.
Доброе утро.
Здравствуйте. Наверное, всем нам уже надоела вся эта история с Zoom во время ковида. Давайте на вас посмотрю, с кем я собираюсь все-таки общаться. Говорить просто в ящик, честно говоря, очень грустно. Если вы в неглиже, наверное, тогда не включайте. А если в глиже, то лучше включите, пожалуйста, камеру. Вот я вижу, что есть народ в аудитории в квантовом центре, да? Ребят, сколько вас там? Я вижу двоих.
Нас трое, но вот уже четверо.
Угу.
Они сейчас подойдут, просто они чуть припаздывают, скорее всего.
Подождать тогда немножко, как лучше?
Я думаю, минуты 2-3 можно подождать, наверное.
Давайте подождем. Остальные категорически не включают камеру. Хорошо, ладно. Хотя нехорошо. Все завелись забавными картинками за время ковидных лекций. Да. Хорошо, давайте начинать все-таки. Давайте я расшарю свой экран. Хорошо. Давайте сначала с кем не знакомы познакомимся. Меня зовут Алексей Устинов. Значит, у вас 5-й курс, ребята. Кто-то из вас слушал, наверное, лекции, возможно, по сверхпроводимости, которые я читал в весеннем семестре для 4-го курса. Откликнитесь, пожалуйста, кто-то слышал или нет. Для меня это важно знать, чтобы понимать, насколько серьезно потребуется введение во второй части моих лекций этого курса.
Да, слушаю.
А сколько примерно, ребят, вот будет, ну, не знаю, сколько всего будет примерно, и сколько слышали курс? Ориентировочно, можете мне сказать?
И может чуть больше половины слушаю.
Чуть больше половины – это с физтеха, да? А вот меньше половины в чате.
Да, да.
Понятно. Здесь участвуют еще студенты МИСИС. Сколько примерно студентов МИСИС планируют участвовать в этом курсе? Кто-то знает?
Ну, нас всего, получается, 16 или 17 человек. То есть я не знаю про своих одногруппников, слушали ли они курс лекций. Но вот половина из этих 17 людей точно не слушала.
Ну, хорошо, ладно. Значит, тогда все равно я оставлю какое-то впечатление по сверхпроводимости в середине курса. Это будет примерно через пару недель. Хорошо, давайте займемся нашей сегодняшней работой. Значит, у нас сегодня 2 пары. Я написал Насте вопрос, на каком языке читать лекции. Вот. И, может, вы мне, поможете в этом? Год назад я читал этот курс по-английски. Это была такая просьба, ну или, скажем так, переводчик. У вас есть ли какая-то программа обязательного чтения вот этого курса по-английски? Кто-то знает на физтехе?
Но все курсы нам стараются читать по-английски.
Все курсы стараются читать по-английски. Хорошо. Ну, тогда, наверное, попробуем по-английски. Значит, по крайней мере, я думаю, что сегодня мы начнем по-английски. Но дальше, если все-таки будут какие-то сильные пожелания и согласие организаторов, я готов перейти на русский. Вот. Ладно. So let's switch to English. My name is Alexey Ustinov, as I said. I'm professor of experimental physics in Germany, in Karlsruhe Institute of Technology, where I'm actually now. And simultaneously, I'm also leading a group at Russian Quantum Center and also teaching some courses at FISTECH and MISIS. Now, the topic of the course is solid-state quantum computing, which means that we are going to talk about solid-state technologies, semiconductor, superconductor technologies, which are possible to realize quantum computers. We'll move this way here. So this picture is just to entertain you. Let me go to the plan of the course. So we will start today with a basic introduction into quantum computing. And then I'm going to spend the second lecture of today introducing to you atoms and ions. And then we'll also talk a little bit about other types of qubits, which are not solid state, not condensed matter. These are photons, which we'll address in 1 week. Then we'll switch over to semiconductor devices and talk about quantum dots, talk about impurity spins in semiconductors. So basically using impurities as for encoding quantum information. And then the last part of this introductory qubits in solid state will be nitrogen vacancy and V centers. Also talk a little bit about fullerenes and electrons on surface of liquid helium. So this is a kind of superficial and introductory part, because really quantum computing until now was not demonstrated using these platforms. I'm talking about condensed matter qubits, which are bullets like third and fourth. Therefore, when talking about solid state qubits, we'll nearly completely focus on superconducting qubits, where quantum circuits, quantum processors have been already demonstrated in many places around the world, also in Russia. And we'll talk about various types of superconducting qubits. I'll give you the introduction into superconductivity in Josephson junctions, which will be, for some of you, a repetition of a fraction of my lectures on superconductivity, which took place this spring. Then we'll switch over to charge qubits and transmon qubits. Transmon is the working horse of majority of superconducting quantum processors nowadays. But then also talk about not only the existing technology, but talk more about more interesting physics and future. And here, devices as fluxonium, so special type of flux qubit, and also elements like superinductance come into play. Now, the superconducting qubits are very non-ideal nowadays, because they suffer from a variety of problems. And the major problem is their limited coherence. So we'll talk about, one lecture we'll spend on working on the coherence and discussing the microscopic mechanisms which limit the long lifetime of superconducting qubits and limit their error rate. And then in the last part of the course, we really go to a bit more advanced topics concerning the various ways of reading out superconducting qubits, talk about their manipulation, about the errors, their origin, and the ways to avoid errors, the ways to handle errors, so-called quantum error correction schemes. And also open a few topics concerning quantum simulation, which is not necessarily universal quantum computing, but it's more broad topic associated with understanding the quantum mechanics. And we will have also a lab tour, which I would be happy to do for you at my lab at MISIS in Moscow. When to do it exactly, we should probably discuss. I'm not sure I can be physically present for the tour, but I plan currently to be physically present for at least 2 double lectures. So we'll have the lecture of today and next week online. And then September 15, there will be no lecture, because unfortunately this time I will be in the plane flying to Moscow. And then there will be 2 lectures on November 22 and November 29, where I hope to see you all in person at Skopje. And then we'll continue with the last few lectures online. So the exam for the course will take place most probably in the beginning of January. Still, the date needs to be discussed with Nastya and Diana, so she will talk to you and find appropriate day which will overlap also at convenience with my schedule. That's the plan at the moment. So any questions concerning the organizational part from your side? I do not monitor, somehow I do not see the chat here, but the chat is empty. Okay, I see the chat. All right, if you have any questions, please put them in chat. And if I don't see it immediately, I will check it before closing the lecture or before the break. But you're also welcome to interrupt me and ask a question directly if you want. All right. So this is a slide which I show in a similar lectures in Germany. So this AG stands for Arbeitsgruppe in German. So this is my lab, but topics which we work on in Moscow and in Karlsruhe are not, of course, identical, but they have a certain overlap and some interaction. So in Moscow, mostly we work with simple circuits demonstrating gates and demonstrating simple quantum processors. But there is also wider topic range opening up in different projects. In my lab in Germany, I work on devices using superconducting quantum circuits for quantum computing, for quantum simulations. We have pioneered the field of quantum metamaterials, starting from the first quantum metamaterial realized in our lab in 2000. The lab is most well known in the international community for our works on two-level defects. And that's what you see here on the right. You see my pointer now, so this is what you see on the right. This is the spectra of multiple microscopic defects coupled to superconducting quantum circuit. We'll have a lecture about that in our course. We also work on hybrid quantum systems, combining different type of quantum properties from different platforms, and also work on the technique which is called laser scanning technology. Now, the superconducting quantum circuits, they require fabrication. They require nano and micro fabrication using tools conventional in semiconductor electronics. That means we need a clean room, we need evaporators to make thin films of superconductors. We need high vacuum to be able to control the pressure of oxygen, which we use to form tunnel barriers on superconducting circuits. And all that is available in my lab. It's in a clean room in Karlsruhe. At MISIS and in collaboration with Quantum Center, we are closely working on developing, setting up the clean room fabrication facilities. There is a new clean room recently finished at MISIS, and many opportunities to do practical work if you would be interested. For superconducting circuits, this could be also an opportunity. We also closely collaborate in Moscow with the group of Oleg Astafyev, the laboratory which is in Laboratorny Corpus and Fistech. At the basement, Oleg has been setting up this lab and over several years, and this has been very successfully working. So his group and my group closely interact also in the programs and projects related to superconducting quantum circuits in Russia. All right, so this is just for you to have an idea from which corner I'm coming from. I also can tell that I graduated from Fistech in 1984, and then did my PhD in Chernogolovka, and then went to work around 1989 to work in the lab in Germany. And then since then, I've been changing a few places before I landed as professor in Germany in 1996. I changed to different universities, and over the last 14 years, I am at the University of Karlsruhe, which is now called Karlsruhe Institute of Technology. That's enough for the introduction, I think. Let's start with the course. Now, what are the requirements? I trust, of course, that Fistech students, they completely fulfill the requirements. You know quantum mechanics already, and you also have heard solid state physics. Some of you have heard also my introduction into superconductivity, which was the spring semester, this spring semester. Now, requirements for the students from MISIS are the same. However, I'm not sure that all of you have heard of this. I mean, maybe some fraction of that you have heard, but you may need to make some reading to be able to really kind of fully appreciate the contents of the course. So these are requirements which actually are strongly recommended for you to follow the course. And if you have some gaps there, please catch up. Quantum mechanics we need in the basis of foundation of quantum mechanics 1, non-relativistic quantum mechanics, including stationary Schrödinger equation, time-dependent Schrödinger equation, the spin dynamics, two-level systems, and this kind of things. Concerning the literature, there are some upcoming books in the world, which of course will be also available online, but there is no systematic curriculum to study quantum computing and solid-state quantum computing in particular in kind of same way as you study other fields like conventional courses of physics. So there is a kind of well-known, one can even call it the Bible of quantum computing, which is a book of Nielsen and Chuang, which is Quantum Computation and Quantum Information. It's not really discussing different platforms. And for example, superconducting quantum computing at the time of writing a book around year 2000 even didn't exist. So it was just made in 1999. Alex Zagoskin, who is a professor at University of Loughborough in United Kingdom, wrote a book which is called Quantum Engineering, which partially reflects the state of the field that time back roughly 10 years ago. But most of the information you can catch from lectures which are available online from different sources. And I recommend several review papers, which I will also put in the shared folder, which you can take and read in it. Some of them are written in a very introductory way. Some of them are in an advanced way. This is the introductory paper, which is called Quantum Engineer Guide to Quantum Superconducting Qubits, written by a team from MIT, led by William Oliver. Actually, the field is not just physics anymore. So to be able to understand and appreciate and handle quantum computing, you need to have knowledge not only in physics, but also in the subjects which are gathered under the umbrella of quantum engineering. Quantum engineering is a combination of knowledge in physics, in electromagnetics, electrical engineering, circuits, higher frequencies, technology, also in programming, to some extent in algorithms and so forth. So this combination of mathematics, physics, engineering, material science, that's something which is called quantum engineering. So quantum engineering program is something new, which actually for the first time in Russia, we are setting up now in MSIS. So there is a kind of new study direction, which will start in the next year. We plan, this we will call quantum engineering, but for you as physicists, most of you are physicists, this will be, of course, kind of call to get extra education in some fields which you not normally know about. For example, microwave engineering, understanding how electromagnetic waves propagate, how they can be handled, what means impedance matching and so forth. This kind of things which are taught, being taught by professors at engineering schools, but not necessarily for physicists. And this is required in this field to be able to follow. So as I said, I will put some of those review papers in the shared folder. I can recommend you this review, which is written, this kind of overview, Quantum Computing Progress and Prospects, which is a paper written by many authors, and it reflects the state of the field back 3 years ago, and also discuss different platforms. It's a very kind of descriptive story, but it gives you an overview which platforms of performing quantum computing have what are their advantages and disadvantages, what are their handicaps and priorities. And that's a kind of interesting to read. There is a similar paper which I will also put on archive on this shared folder, which has been written by Alex Fedorov, Alex Lvovsky, and Sergei Belousov. This paper, which is more written for kind of technology investors and businessmen who are interested into the field. So it doesn't contain much physics, but contains a lot of discussion concerning the advantages and disadvantages of different approaches. So that's something which is similar to this kind of quantum computing progress and prospects overview of the National Academy in the US. So look into this folder, you'll find some interesting reading there. Actually, I wrote to Nastya this morning to provide me a link, but she didn't. She will surely do it and also share with you in the next days. Any questions to the literature? Any requests, comments? Okay, not the case. Then let's start with introduction. There are many materials you could read on the internet about quantum computing. If you just Google quantum computing, you will get a lot of information, which was not the case only 20 years ago. It's really a rapidly developing field. And the field changed completely, and it became much more engineering than only physics around 2014, when actually Google hired the whole group of university professor John Rapinis from the University of California in Santa Barbara to work on their project to build a quantum computer. About simultaneously, maybe 1 or 2 years earlier, a similar effort was started by company IBM, which first came up with a very simple, technically useless, but very interesting for demonstration, 5-qubit processor. And then they scaled it up to 16-qubit processor, and then 20, and then 50, and nowadays they offer over 100 qubits for their customers, and they have quite a few customers also. For example, Fraunhofer Institute in Germany bought an IBM quantum computer, and they're trying to do something useful with it. Of course, the usefulness of quantum computing at this stage of development of technology is very limited. So for commercial applications, may be useless even, but what is very encouraging is that you could really attack problems which cannot be addressed at all by classical computers. And this has been demonstrated in a seminal experiment performed by Google team in 2019, where they for the first time demonstrated so-called quantum supremacy or quantum advantage. So they were able to make a circuit which performed quantum, we call it simulation, a quantum computation of a problem which is not treatable at all on classical computer. And the claim that time was that what they did in 20 seconds on this processor was requiring 10,000 years on the classical computer, on the best supercomputer in the world. Well, the specialists from the company IBM, who were competitors to Google and remain competitors to Google nowadays, they corrected them that, well, do it properly on a supercomputer will require much less time, only 2.5 days, but nevertheless, 200 seconds and 2.5 days is a large difference. So I think now, 3 years after, we can say that this experiment really demonstrates quantum advantage. However, the computation which was made there was completely useless. So there was nothing practical in that. So only the fact that the problem, which was compared with classical simulation, could not be solved on the classical computer. This was only claim which was maybe interesting for demonstrating the limits of this approach, demonstrating the validity of the approach. But the only application which the authors can think about excuse me. Can think about that time was a random number generation, which is of course not much. So we'll talk about this a bit later, because we in the major part of this course will discuss superconducting quantum circuits, and you see here the head of Google touching the inner part of the refrigerator, which is the large cryostat with temperatures where the whole thing is closed. It goes from room temperature above to about 4 Kelvin here to 1 Kelvin here, and then down to about 20 millikelvin at the lowest temperature stage. And this whole computer is located at very low temperatures. Why? That's something we are going to discuss later on in this course. If you Google quantum computing, often you come across with a company which is called D-Wave, which builds the so-called D-Wave quantum computers. Now, just to orient you a little bit, D-Wave is a company which was first offering commercial quantum computers, starting from roughly, I believe, 2007 or so. Actually, what funded my group for some time before that. Now, the device which they developed is not a universal quantum processor. It's not a processor which works with quantum gates, quantum algorithms. It's the so-called annealer device. So it's a device which is performing so-called quantum annealing, which means that it's a quantum simulation where a certain type of Hamiltonian can be modeled by manipulating currents sent through this circuit. But nowadays they have over 5,000 qubits, and they claim their commercial applications are on the way. Still is very limited number of users there. And I would say that majority of physicists whom I know around the world are not fully convinced that this device is quantum. It can be partially quantum, can be considered as partially quantum. But even the quantum advantage of using this simulator is still being debated. So it's not something we are going to talk about in the first place, but partially these devices were also based on principles which we are going to discuss in this lecture course. All right, so this is just for you to sort of give the, to flash quickly what is the state of technology which is based on the physics which we are going to discuss in this course. Now let's start with the first lecture. So the first lecture is actually will be a broad introduction into quantum computing, something which you have already heard, I believe, in some of the previous lectures. Some of you may not have heard because the audience is a little bit mixed, but, as I understand here. So some of this is going to be a repetition, but you will hear my version of that. And it's not going to be a difficult lecture. I believe something which will come later is going to be a bit more advanced. All right, so first slide is really simple. Back 200 years ago, no one even thought of anything besides abacus, shooting. When I was a boy, I have not seen any other instruments in the shops around 1960 plus. It would be just this device counting the numbers. And for these numbers, this device people were using for about 3,000 to 4,000 years. They were invented a very long time ago. But then what happened in this in the previous century was really amazing. Now we have computers and not just doing the calculation, but they're doing everything for us. And that's something which is really fascinating in the revolution. Few words, how computers came about. That's interesting story because looking back into that, one can also sort of make a parallel what is the state of the art now of quantum computing and what can be the future of quantum computing? What should we expect? And looking back into the normal computing, goes back into the beginning of the previous century, and first person to name is often Alan Turing. So Turing machine is the thing which you learn in the informatics, studying the basics of programming and so forth. And in 1936, he published his famous work on computable numbers with an application to Entscheidungs problem. Alan Turing actually was a pioneer there, but he was, of course, only working on theory. And that time, the ideas which he put forward were difficult to realize. So that time there were, of course, mechanical switches, and that's something which people learned to use to switch between states 0 and 1. But about that time already, electrical applications were on the way. And one of the first applications was the switch which was controlled by external voltage or external current. This was a relay. Electric relays were around since the already First World War, of course. And one of the persons who really contributed immensely into development of the hardware was a German engineer, Konrad Zuse. He's less known outside Germany. In Germany, there are streets which are named after him. He has been also living for many years here. But he was actually the first one trying to realize something which was kind of built on the based on ideas suggested earlier by Alan Turing. I think Zuse learned about these ideas on the way when he was already making his first computer. Actually, his first computer was decimal and not binary. And then he realized that decimal is too complicated, so one has to go back to some simple circuits which can be scaled up and to perform also decimal calculations. Now, his first computer, which was called Z1, was actually the first world programmable computer, which evolved into the Z2 and Z3, which was already using partially vacuum tubes. But all these devices, unfortunately, were destroyed completely because Zuse was living and doing his experiments in Berlin, and everything was destroyed under bombs in the Second World War. But then Zuse was not forgotten. Actually, he started a company which didn't really develop itself too far, but it was acquired by industrial companies and finally was acquired by Siemens. And much of his work actually and ideas were saved for technology. Now, key development actually in computing should be acknowledged to John Neumann. He formulated the operation principles of computers and actually named relevant parts for the computer. So he named that the computer should have a processing unit, should have input and output tools, should have memory, and all that actually was the basis of building modern computers. It's very interesting that actually John von Neumann, between many other things, you know that he was actually responsible for breaking Enigma, using Enigma, the code of Germans during the Second World War, which allowed actually Britons and Americans to hear to get all the information concerning the military activity, in particular in the sea. He is also known, John von Neumann is also known for laying down the mathematics of quantum mechanics. So he has been working on the field which is basically introduced the concept of Hilbert space, not space itself, but he introduced the concept that a quantum system state is just a point in Hilbert space. And then he also used the matrix theory to describe the evolution of this point in the Hilbert space by applying matrices and introducing unitary matrices as a formalism for quantum mechanics. So quite an outstanding person. But back to the hardware, because our subject here is a hardware, so Zuzu was really one of the key persons. And the ideas which he was working on were in parallel developed in the US, where the first powerful digital computer was built as early already as in 1946. And you see this computer called ENIAC operating in, I believe, in Pittsburgh in the US at that time. So it consisted of thousands of vacuum tubes, which were used as switchers between 0 and 1, so this was a binary computer. And I guess what was the main job of people who maintained this computer? They were actually replacing the failing parts. They were replacing the vacuum tubes which were defects, and they were going defect very frequently. So this computer was actually never working for a long time. It was just working for some time, and then but has to restart the calculations because there were errors coming in because of broken vacuum tubes. But nevertheless, this computer was actually powerful enough to be able to do calculation of the ballistic tables. So these are tables for artillery and missiles. If one wants to calculate the trajectory, these are ballistic tables done. Were used for that time, and calculating those tables for new weapons was very time consuming. So this computer was able to do it much quicker than humans can do it manually. And then further application of this computer was actually using it for first weather forecasts and also for a variety of other simple problems. So computer wasn't really used for too long time. I think it was stopped being in use in the beginning of 50s. About that time, an important event came about, and the first transistor appeared. And this was actually made first by these three gentlemen, Badin, Batten, and Shockley in Bell Labs, where they were able to show that this actually device can have some gain, similarly to a vacuum tube, and can be made in a compact way. Moreover, they already at that time understood that it can be scaled up in larger numbers because one can reduce the size of transistors by various techniques and then make many transistors on the same chip. And the development of that really led to what we know now. So now we have huge semiconductor chips with huge number of transistors, which are all devices switching between 0 and 1s, and this is the logic which we use until nowadays. And this development was reflected in this exponential plot, which was first suggested by the founder of Intel. This was Moore, who basically said that every 18 months, the number of transistors on chip will double and the frequency will double and so forth. Well, the frequency doesn't double anymore in every year and a half because the signals, they basically reach the speed of light. Just recharging the capacitors and capacitances associated with transistors on chip takes time, and therefore the frequency is stagnated already over more than a decade at the level of about 3 gigahertz. But still the number of transistors on chip continue the exponential scaling. A bit maybe slowed down, but the number of atoms in the modern transistor with 7 nanometer technology can be counted in thousands. So this really shows the limit that you will have only few electrons in this kind of devices, already have few electrons in this kind of devices, and quantum limitations are impossible to avoid. But that's actually, I told you this story to have an overview how primitive was the beginning of the computation back 100 years ago, or even less than 100 years ago. What were the ridiculous looking were the first computers, and how far they are today. So what we are having now with quantum computing is something which is probably the beginning of middle of 50s, maybe end of 50s now, because that's about the time when Americans started making first integrated circuits, putting more transistors on many transistors on one chip. And that's something what quantum computers can do now, do computations with a few tens of qubits. And this number is steadily growing, already entering the hundreds. So that's a process which will continue in technology of the future. And that's something which I think for your generation is very exciting and very intriguing to observe and to get involved in. It's really a technological revolution which is happening nowadays in modern technology, and something which your knowledge of physics can be invaluable to contribute. Okay, let's move on. So now let's talk about quantum. As we all know, the whole world is quantum, and quantumness of transistors, of course, was understood already in the 50s. So band structure of solids based on quantum mechanics. However, individual quantum objects like atoms, like if you take one atom, it's a very interesting system because it's really ideal. You have all atoms in universe identical, and it's intriguing really to use this kind of hardware for doing the quantum some useful tasks, calculate some useful tasks. And one of the useful tasks is calculation of the properties of materials, for example, where one has to translate the quantum mechanics into the classical language because computers which calculate material properties are classical. So one has to use some approximations to simplify quantum problems. And these are approximations, whatever, Hartree-Fock or some other approximations which are being used to calculate material properties. They require translation into classical and then applying these classical results back to quantum. And people thought about this for a long time already. In most of literature, we'll find Richard Feynman, who of course was a famous physicist, and he was actually one who brought this question up to white majority, for white audience in physics. Is it possible to build computers so that you use the laws of quantum mechanics to compute? So just not translating from classical, but only do it all quantum. But besides him, there were other people thinking of that, and in particular, there was a Russian physicist, Manko, who actually, about the same time or a little earlier, was thinking along the same lines and published the papers about that. Anyway, so this idea is rather appealing, and that's why people started thinking of the hardware which can be used to encode information in the quantum. Atoms are obvious, and atoms can be, of course, exist in any material, but in any material they interact with other atoms. So to be able to talk, so to say, to an individual atom, one has to isolate this atom, and this can be done by placing an atom in vacuum, but one needs to make sure that the atom doesn't fall down or fly away or is not lost. So to do this, one can use so-called optical lattices, which we'll talk about briefly in the lecture, in the next lecture. There are, of course, also photons, which are massless particles which propagate very freely. The disadvantage of photons is associated with the advantage. They keep their quantum states for a long time, but they are not much interacting with the rest of the world. So to make photons in particular interact with one another is a very difficult task. And this interaction is very limited and can be only achieved with materials with a so-called Kerr effect. And one really requires some hybrid systems to use photons in as quantum building blocks. Something we'll talk about on the second lecture of today are ions. You may have, of course, heard of this. I will give you some brief overview, a bit superficial, of ions technology, where charged atoms, basically atoms with one or more electrons stripped away. They can be also trapped in free space by using electromagnetic fields. But the most promising are approaches using solid state. And that's where a lot of things have been happening over the last decade. So there are approaches using semiconductors. We'll talk about them briefly. There is a recent progress achieved that, but so far most complex circuits are only 2 qubits, though with very high fidelity of gates, one has to admit, and there is a promise to move forward using the whole background of semiconductor technology which exists and is available. But the field which is very interesting and very unique in a sense, and very which made very quick progress, is the superconducting quantum computer, which actually is the field of my research and the subject also of the most part of the lecture of this course. So these are different qubits which can be used. The list can continue. There are many candidates which people propose and proposed before and keep proposing now. But the number, of course, is not exhausted yet, and there are many still interesting ideas to come. Now, why making quantum computers difficult? Well, the problem is that to be able to do the quantum computation, you need to control something which is quantum and which is very gentle. So if you take an atom and you put an atom in electromagnetic fields or other fields, even gravitational fields, the state of atom is changing. And if you know how the state of atom is changing, you can take this into account. And actually what you do to quantum compute, you change the state of atomic-like systems. You change the quantum state by applying certain fields or forces to manipulate the quantum state. However, if this happens in uncontrolled way, something which you cannot follow, just to the interaction through environment with other atoms, other spins, and so forth, then this initial state information is lost, and your manipulation will not give the result you want to achieve with the same fidelity. So these uncontrolled effects which occur from the environment, they're called the coherence, and they limit the so-called memory or lifetime of quantum states, which means the lifetime, the time which you can over which you can reliably predict according to the laws of quantum mechanics, the state of a quantum system. And the coherence, it leads to errors. So the whole kind of agenda of building quantum computers is actually fighting with the coherence. It's not only the coherence, of course, that you need also to be able to do the manipulation. You need to read out the quantum information, and we'll talk about this later on today. But the coherence really is the biggest problem. And therefore, many proposals of building quantum computers, they were built based on the systems which can be made more or less coherent. And for some of them, it was not known how coherent they are. Like for superconductors, 25 years ago, it was impossible even to think that they can be quantum coherent in the sense of atoms. But trying by doing actually brought physics really far ahead. And now we know a lot more about coherence, also quantum mechanics, and also the ways to preserve the coherence. So let's start with a very basic slide. You may have seen it before. Actually, I see it all around. The slide I made maybe 15 years ago myself, but it now being present in many lectures of my colleagues around the world, just because probably it's very simple. This slide emphasizes the difference between classical bit of information and quantum bit of information. In a classical sense, in a classical computer, we encode information in 0 and 1s. And this can be level of voltage output of a transistor, 0 volt or 5 volts. But in principle, if you go back to the binary architecture of first computers, then you need just 2 states, and you need to be able to switch between those states. So you need the state 0, which can be location of a particle in one potential well on the left. And you could call, for example, the state 1 if the particle is located in the state 1 on the right well. And if you are able to switch between those states, and the states are not being mixed by errors, for example, there is there is no noise or noise is very small, so there is no switching between 0 and 1. random switching uncontrolled. Then there's basically the hardware which you can use to operate a classical computer. Now in quantum mechanics, things are different. If you make now a double well potential, and you know this, or you should know from quantum mechanics 1, properties of spin 1/2 system. If you have spin particle with the spin up and spin down, if you measure this particle, you either measure spin up or spin down, nothing in between. However, this particle is in superposition of the two states. And the superposition is described by potential, where at zero magnetic field, these two states, spin up and spin down, are both possible with equal probability. However, due to the quantum nature of the system can be described as this double well potential, where the states on the left well and right well are coupled by tunneling. Tunneling is a quantum mechanical process which in principle can be coherent, and the tunneling leads to the fact that the particle in the left and right well exists in the superposition of the left and right state. On the other hand, if one solves this problem using the Schrödinger equation and then diagonalize the problem, one gets the eigenfrequencies of the system, and it comes to the conclusion that the eigenfrequencies are associated with the two low-lying states, 0 and 1. And the states are stationary states, so if you prepare 0, it will stay forever. The state 1, in the absence of relaxation, also will stay forever. However, the wave function of the state 0 is this antisymmetric, so is this symmetric superposition of left and right, and the state 1, which is the first excited state, is the antisymmetric superposition of the left and right. So you are back now to this different basis of eigenstates of double well potential. And of course, also there are higher states. There are states which are somewhere high up here, but we even don't discuss them because they are high up in energy. And if we use, for example, photons to couple states 0 and 1, for example, we can apply a photon to this system, and the photon will get absorbed and will go from state 0 to state 1. So we'll go from symmetric superposition to antisymmetric superposition. So this is the physics of spin 1/2 particle, which is described by this type of wave functions for the eigenstates. And any possible state of this two-level system, if we ignore the higher levels, we say that we don't have any processes which bring us so high up on inner energy, so that the only two states are important. Any state can be described as a superposition of 0 and 1. So we have this wave function psi is equal to alpha times 0 and beta times 1, where alpha and beta is the vector with complex coefficients, which describes the state of the two-level system. It's very convenient to present this state on the so-called Bloch sphere, which you should remember from quantum mechanics or from magnetic resonance classes, where actually we describe by Bloch sphere spin 1/2 particle and describe also manipulation about the spin 1/2 particle. So this applies to nuclear magnetic resonance, applies to electron spin resonance, which we call paramagnetic resonance, discovered in Russia in Kazan. So basically, all those resonance techniques are describing spin particles state on a Bloch sphere, and here the upper state is often named as 0, or we could call it North Pole of the Bloch sphere. The lower state is pure state 1. And then any superposition of those two states will occupy a point on this sphere with the radius of unity. And one can see that we have these two coefficients, alpha and beta. So they are complex numbers, but due to the fact that the sum of alpha square plus beta square is equal to 1, according to normalization, the allowed coefficients of alpha and beta are such that the points describing the states will be lying on the sphere. One can make a transformation in variables and go from alpha and beta to new variable, which will be theta and phi. and this will be a polar angle theta and azimuthal angle phi. And by then, basically, we describe the wave function now in these new coordinates as written here. So this will be this coefficient, real coefficient applied to state 0, and then this coefficient applied to state 1. So, of course, normalization also holds here. Now, it's interesting that the global phase here is not observable. So it's only when you fix the phase phi in the initial moment, you would be able to follow the change. So the variation of this angle, of this azimuthal angle, is the rotation around the equatorial plane of the Bloch sphere, and then rotations around x-axis or y-axis will be changing the projection on the z-axis. This will be then changing the probabilities of states, but not their phase, states of 0 and 1. So when we do the measurement of spin 1/2 system, as we know, as I already mentioned, you measure either spin up or spin down. So you either measure state 0 or state 1. Now we talk about different bases. Of course, first I talked when measurements, I talked in the basis left and right. So either spin up or spin down. Now here we talk already in the basis which is in transformed variables where we have diagonal as the Hamiltonian. So there's eigenstates 0 and 1. So when talking about manipulation of qubits, you need always to think in which basis you describe the physics here, in which variables. And when you do a measurement, you either can measure direction of the spin, which will be left and right, or you measure in this picture if you are in the state, in the lower energy state, or in the high energy state. And this will be then basis 0 and 1. So these are different measurements. And typically, the measurement of a qubit in this kind of level of abstraction will distinguish between state 0 and 1. And again, if you do the measurement, you destroy the quantum state, you make a projection of the quantum state, and with certain probability you measure 0, and with certain probability you measure 1. If you have prepared the state 0, you will 100% of time measure the state 0. If you prepare pure state 1, you will 100% of time measure the state 1. However, if you prepare the state which will be on the equatorial plane, then of course the 50% probability you'll measure the state 0, and 50% probability you'll measure the state 1. And this kind of measurement actually collapses the wave function, and superposition is destroyed. So basically, you need to start the whole process of preparation of this state again, and then measure it again to gain the statistics. That's the usual process of quantum measurements, and this probabilistic nature means that you need to manipulate the qubit many times, 100 times, 10,000 times, and then measure the average outcome, average probability of one state or the other. There are also other types of measurements, so-called weak measurements, which we will not talk about in length, but there are also techniques where we, in this course, address this a little bit when one does the so-called measurements of quantum trajectories and so forth, where the quantum state is not completely destroyed, it's only partially changed during the measurement. All right, then as I mentioned, there are different bases, so one can measure in the basis of 0 and 1, but can also choose some other basis. For example, one can measure projection on the x-axis, one can measure projection on the y-axis. And then transformation of variables will be such that this will be the representation of this basis through 0 and 1s. This can be stated as basis plus, and this is basis minus. It's often used in literature as well. Or in particular, when we talk about rotation, we use Pauli matrices, sigma z, and so forth. One can also use the combined Pauli matrices, plus and minus. This is similar notation as here. Now, if you measure, for example, if you prepare the state which is like a pure basis state like this one, and the other state which is opposite to that, they're distinguishable in the basis of axis y, but they're indistinguishable in the basis 0 and 1. So one has to pay attention on that when choosing the basis, basically by when doing the quantum computation, one applies some preparatory pulses, like rotation by 90 degrees around certain axis, to be able to measure the state in desired basis. And this is something which we will talk about later on examples when we talk about different systems. Okay, so this is things you certainly might have heard before concerning manipulation of spin 1/2 particle or two-level system on a Bloch sphere. Now let's talk about computing. When doing computing, in classical computing, we have the so-called gates, ventili. And these gates are basically simple things like you have operation not when you convert 0 to 1, or the same operation converts 1 to 0. There is also operation OR, which can give one output depending on the state of 2 bits, or operation AND, and so forth. Now, in classical computer, for example, these particular operations like OR and AND, they are not reversible. You have the output of 1 bit, and you cannot recover the initial information. So the information is lost. So classical computer is not reversible. Quantum computing is reversible computing. And it's kind of particular case of quantum computing, of reversible computing, which is also existing classically. At least the ideas exist how to implement this reversible computing classically. And this computing is also based on gates. So to say very simple, quantum gates are rotations on the Bloch sphere. The Bloch sphere describes two-dimensional Hilbert space. There are 2 dimensions here because you require only 2 coordinates on Bloch sphere, phi and theta, azimuthal and polar angle. In the case of single 2-level system, you have this 2-dimensional space, and then you basically rotate this state of the system, rotate the Bloch vector on the Bloch sphere over around different axes. And one of the well-known example is the so-called Hadamard gate, which is described by this matrix of rotation of the vector. So you multiply basically the initial vector of your state, alpha and beta, by this matrix, and you get a new state of the system. And intuitively, it's shown here what it does to states like state 0, initial state with the on the north pole. It rotates to the horizontal axis along x axis, and then if you have the state 1, then the same operation applied will rotate the state also to the equatorial plane on the opposite side. So basically, by applying the Hadamard gate, you can go from the basis state 0 and 1 to the basis state, which I introduced before, plus and minus. So this is just one example. But there are also other examples, many other examples of how you can rotate. In principle, there is an infinitely large number of ways of rotating the point on the Bloch sphere. You can use a combination of different gates to come from one point of the Bloch sphere to the other point of the Bloch sphere. And this is just a formality, which kind of set of gates you will choose for your quantum manipulation. So there is a NOT gate, which basically brings the point from one end of the Bloch sphere to the other. For example, if you have the state 0, you will get the state 1. But if you had the state in this point of the Bloch sphere along the x-axis, state plus, you'll get to the state minus. So it's kind of universal gate, which rotates the vector on the Bloch sphere. When doing this gate, this NOT gate is often called a pi pulse. Why, I will explain to you in a moment. There is a Hadamard gate, which I just introduced, which is rotation by pi over 2, but this rotation can also happen along other axes. So there are also other types of rotations, which are all described by the pi over 2 pulses, and then depending on the initial phase, there will be rotation along particular axis. And there is an arbitrary rotation, which is called the phase gate. And this is interesting. For example, if one has a double potential and for a short time makes this potential asymmetric, slightly asymmetric, this changes the energy level separation. And if you go back to quantum mechanics and look what happens with the quantum system, if the energy level separation between two eigenstates is changed, it actually means that the state of this two-level system, basically the state described by alpha and beta, acquires a phase which is proportional to the variation of energy divided by Planck's constant times the time. So this is the factor in the exponent which comes into the which is identical to the phase, and basically this means that by applying this little z field for the spin 1/2 system, one does not change the population of the two states 0 and 1. The states themselves slightly change in the energy, but what changes is the azimuthal angle phi. So you'll have a rotation over the azimuthal angle, and if you prepared the state in the equatorial plane, like for example here, this will mean just rotation along the equatorial plane. And then depending on the time which you wait, you will have a different phase accumulation. Here you'll have different phase gate. So this is basically a rotation around z-axis of the Bloch sphere. So all these are single qubit gates which can be implemented in conventional magnetic resonance technique as nuclear magnetic resonance or electronic paramagnetic resonance. Now, to do the quantum computation, having just single qubit gates is not enough, and that's something we'll talk about in a moment. Now, Pauli matrices describe particular gates. Actually, these are particular single qubit gates. They are often in quantum algorithms described by these circuit symbols. So this is like applying to the qubit sigma x rotation, this applying sigma y rotation, this applying z rotation. And if one has the magnetic field which one applies to a spin 1/2 system, one can introduce into Schrödinger equation, of course, stationary Schrödinger equation, this kind of potential which is introduced by field. And this basically described then by this matrix, this Hamiltonian, which can be split into the representation of the sigma x, sigma y, sigma z operators. It's quite often that sigma x, sigma y, sigma z being used to describe quantum states of qubits. So it's a good idea to repeat this for your knowledge if you prepare yourself for next lectures of this course. And one of suggestions easy to read is Feynman lectures of physics, of course. For example, corresponding chapters 10 and 11 of volume 3. I think in Russian edition, it's volume 8 at the very end. It's ammoniac molecule. All right. Now, how to do this gate in reality? Gates in reality. Well, the technique which is standard for the two-level system, which has two levels separated by certain energy difference, is the so-called Rabi rotation. Rabi oscillations are named after Isaac Rabi, who got his Nobel Prize many years ago. And basically, he understood this very important phenomenon of atomic physics, that if you have two states and then you drive the system at the frequency of the transition between the two levels, so basically you have the energy difference between the two levels, you divide this energy difference by Planck's constant, you get the frequency, basically get the energy of a photon, which you need to come from one state to another. But now you drive with classical field. You drive with classical field, you drive quite strongly. This could be electric field, for example, or magnetic field. Just electromagnetic field, by the way, applied to atom. Then the system will coherently evolve between the two states. So if you prepare initially your system in the state 0, it will coherently go to the state 1 and then back to state 0 and state 1 and state 0. This is under assumption that this field which you apply is fully classical. So it's not really quantum description of that. And then depending on the amplitude of this field, you'll have then occupation of the excited state, which is on this plot is probability 1, and this on the state 0 is the lowest 0 here. Then you will have this rotation around the, for example, x-axis, and then this probability of finding the system with the state 1 will oscillate. Now, you see the frequency of Rabi oscillations. This is now the duration of the pulse of which you apply this driving field. If you change the amplitude of this pulse, then the rotation frequency increases proportional to the square root of the power, which means proportional to the amplitude of the drive. So if you choose particular amplitude, then you could say that you need just this time of the pulse to bring your system from ground state to the excited state. And this will be the pi rotation, or as we discussed already, this will be not gate. If you drive just half of that time, this will be pi over 2 rotation. This is when you apply these pulses to zero state, but you can apply these pulses to any state. In this case, this will be just rotation according to around the corresponding axis over the certain angle, either pi angle or pi over 2 angle. And this is a standard technique of preparing the states in NMR, and also standard technique at the same time. Same thing for preparing states in quantum bits, in qubits. Now, for doing quantum computing, 1 qubit is not enough. Of course, you have immense resource of information. You don't have anymore 2 states. You have an infinitely large number of states in your 2-dimensional Hilbert space on the Bloch sphere. However, to be able to do quantum computing, and this has been proved by people who made theoretical foundations for that, you need at least you need more than 1 qubit, of course. And besides single qubit gates, you need at least 1 2-qubit operation available, which means that you should be able to do this. And if you describe multi-qubit states, let's start very simply from 2 qubits. Suppose you have now 2 spins which interact with each other, just magnetically. Then we know that there are now, instead of just 2 states, there are more than 2 states. There are 4 states. Namely, one can choose those eigenstates as both spins up, left spin up, right spin down, left spin down, right spin up, and then both spins down. These are states 0, 0, 0, 1, 1, 0, and 1, 1. And then general 2-qubit states can be described now by the wave function, which is a superposition of those 4 eigenstates with corresponding coefficients, complex coefficients alpha 1, alpha 2, alpha 0, 1, 2, and 3. And now the Hilbert space is not 2-dimensional anymore, it's 4-dimensional, because we have 4 dimensions, we have 4 eigenstates and corresponding 2 coordinates for each states. And in general, n-qubit state, if you take n qubits, not just 2, will be a superposition of the 2 in the power n states. So for only 50 qubits, 15 states. And that's really something amazing. So it's an amazing resource of complexity and opportunity to encode the information. So if you have a memory which consists of quantum bits, to increase the memory by factor of 2, you don't need to increase the number of quantum bits by factor of 2. You only add 1 extra bit to n qubits, and then the Hilbert space is increased by additional 2 dimensions. So basically, this is really amazing resource of information storage and manipulation. Now let's go back to something which was the subject of Nobel Prize this year, to entangled states. If you take 2-qubit states, then you can naively think first that you multiply single qubit states and then you get all you need, but that's not the case. These so-called product states are a tiny fraction of the 2-qubit states. Most of qubit states are the so-called entangled states, states which you cannot really represent as a product of individual states of qubits. And one example which is well known is the so-called belt states. And in the basis of 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, let's think of a state which we can assign. We can, in principle, think that we can prepare this state for this 2-qubit state of the previous slide. So we can take basically this state, and we take this state, and then we prepare this with equal weight. and with real coefficient here. This is the so-called Bell state. Now, this state is a little strange. Strange in a way that it doesn't contain any eigenstate here. There is zero probability of measuring one qubit in state 0 and the other qubit in state 1. You can either measure both in state 0 or you measure both in state 1. And for this particular state, this will be with probability 1/2 for each of those states. That means that if you measured only part of that system, if you measured only one qubit, but you know that you had this Bell state, unavoidably, the other qubit is going to be in the state, in the same state as the first qubit you measured. And if you measure the state 1, the other qubit will be also in the state 1. And if you separate those qubits, you make them interact, and you separate them far away, then this should remain valid. And that's something which is actually in the basis of quantum teleportation, that by measuring one part of the coupled quantum system, entangled quantum system, you will know the quantum state of another. And by doing this, you will sort of instantly transfer the information over any distance, not thinking of the speed of light. But that's not something we are going to talk about in this course. We basically now talk about qubits here. Now, another entangled state is the so-called EPR. Don't mix it with electron paramagnetic resonance. It's Einstein-Podolsky-Rosen state, which is well-known state for which Einstein-Podolsky paradox was discussed in the 30s by Einstein and his co-authors, where a similar type of correlation between quantum states was discussed. And most celebrated example of that is the so-called Schrödinger cat, which of course you all heard about, that superposition of macroscopic states of many, many bits. And if you prepare them in such that one combination of bits is corresponding to living cat and the other one is corresponding to dead cat, then basically you can prepare the cat in superposition of life and death. And you know the example which was discussed, this was a decay of radium atom with certain probability that would kill the cat in the case of decay, but will not kill the cat in the case of no decay. Now, just a side comment, there is a whole field of physics actually, which is hunting for cats, building bigger and bigger superposition states of many, many bits. And the size here is not a physical size. The size is actually the number of elementary bits, or if you want, the size of the Hilbert space, where really superposition of many particles, so many quantum objects can be constructed and then observed, and their coherence can be studied. That's actually very interesting, how large can be quantum system until the superposition is broken. And previously, people thought of this very naively, that, for example, a superconductor is a quantum state. All the electrons are in the same state at zero temperature. However, this is not described by individual wave functions of the electrons. It's described by the phase of the whole condensate. And therefore, the macroscopicity of many electrons in the superconductor is not just the size of the cat. So the size of the cat is really the number of elementary quantum states which you bring into interaction and superposition, and then study the coherence between different distant points in the Hilbert space. All right, let's move on. Examples of two-qubit gates there are many, of course, but one of the very well-known examples is the so-called knot. This is the conditional knot which one applies to qubits. And one qubit is being named here as control qubit, and the other is being named as a target qubit. And then, depending on the state of the control qubit, targeting qubit can flip or not flip the state. So if you apply this matrix to this four-dimensional state, then the states 0, 0 and 0, 1 will not change after applying the state, but state 1, 0 will change to 1, 1, because you have to swap the state of the target qubit if the control qubit is on 1, and the state of 1, 1 will change to 1, 0. So as I said, a universal quantum computer can work on the condition that you have at your disposal some single qubit gates. There are many, as I told already, and at least one 2-qubit gate. Either this one or some other, but you need at least one 2-qubit gate, or more than 2-qubit gates at your disposal. Then you can really do quantum computing. And that slide is about generation of the entanglement. So it's sort of something which people not always note, at least don't pay attention, but it's very interesting. So once you have created an entangled state, for example, you created a Bell state, like 0, 0 plus 1, 1. And then you apply just a single qubit operation to qubits which have been interacting and then not interacting again. By changing the state of one qubit, you change the other qubit simultaneously, because you change the quantum state of the entangled system. So you cannot go out of the entanglement so easily. There is a procedure of doing the disentanglement, but that really requires quite sophisticated technique. Typically, you need to reverse operations in time. So in this case, you will sort of make the entanglement back by applying same type of inverse rotations. So by measuring the state of only one qubit in the entangled qubit register, you will be able to determine the states of other qubits, because you really project a fraction of the Hilbert space of the coupled system. And that's really something which Einstein called spukhafte Fernwirkung, spooky action at distance, which really brought him very uncomfortable thoughts, which he was sharing a lot, as you probably read about with Bohr and so forth, about quantum mechanics. But that's more like interesting philosophy of quantum mechanics, which is still being debated and requires human experience beyond daily things to be accepted and brought into our intuition. Now, if you have a classical computer, then, as I said, you have classical gates, which are often non-reversible, because you get 2 bits of information and then you get 1 at the output. And in this case, you run the algorithm with one or more, with some input bits, and you get some output bits. In the quantum computer, the number of input and output bits is the same, which is not necessarily the case for the classical computer. And you get basically, you manipulate the qubits with those rotations, also rotations in the multidimensional Hilbert space, and then you get some output. And then as a result of computation, you basically need to determine this final state, which will be the state transformed from the initial state. So you have multidimensional Hilbert space, then you go from point A to point B in this multidimensional Hilbert space. And that's that point B, which you measure, is a result of your computation. And quantum algorithms have been proposed by different people. You may have heard of those names. One known algorithm is so-called Deutsch-Jose, where you decide whether the coin is faked or real. So classically, you need to look at the coin from one side and from another. Fake coin will have, for example, eagle on both sides, and real will have it's not only one side. So you need to do it twice for the coin, but for the quantum algorithms, you can do it by one measurement or one step. There is also search algorithm, Grover's algorithm, and also well-celebrated Shor's algorithm for factoring large numbers, prime numbers, which are the basis of a RSA protocol used for conventional, for modern cryptography. Well, that's something which was motivating the development of quantum computers. Now, those algorithms, all of them have been implemented in real quantum computers. On simple terms, for example, Shor algorithm was implemented to factor numbers like 15 or 20, 20 plus. But practical, of course, applications where these algorithms will become important are still on the way and not have been achieved so far. So the idea of quantum computing, as I said, you start some initial state of your multi-qubit register. Then you execute algorithms by applying single and multi-qubit gates. And then you read out the result. And this all needs to be done in a time which is still short enough compared to the coherence time. So you should have your quantum memory not fully broken. So if you wait too long, then the coherence will create errors and the result will be not precise. But it's interesting that if you get the precision, not 100%, but even 80% for many of the computations, it's already very, very valuable. So it's something which many people, including myself, back some years ago, completely misunderstood, that actually quantum computer can be also good if it does approximate calculations. So if it calculates the result with only limited fidelity, not 100% fidelity. That's quite interesting. And this probably is my last or pre-last slide. Maybe I will stop here and start next lecture from this slide, just to have a break. Now, I need your help because I got no table of your courses. We are now 1.5 hours through, so it's 12 in Moscow now. What is your time for the break? Can you tell me, please?
Ну, вообще 11:50.
50?
Да, в 11:50 перерыв.
Ага, извините, что я затянул, просто я думал, что 1,5 часа ровно. Так, значит, потом перерыв какой у вас в 11:50?
В 12 начинается следующая пора.
Хорошо, давайте сейчас сделаем перерыв до 12:10. И следующую лекцию мы тогда сделаем сегодня покороче. У вас, как я понимаю, там еще сегодня что-то есть, поэтому я не должен затягивать, чтобы успеть вписаться. Хорошо, перерыв 10 минут.
Можно вопрос задать?
Да, пожалуйста.
А вы можете вернуться на страницу с раби-осцилляциями, с
Да, конечно.
пульсами, все вот это вот?
Да.
Вот, да, видимо, вот это. Ну, просто давайте временно забудем про сферу Блоха и рассмотрим атом, который может находиться либо в основном, либо в возбужденном состоянии.
Да.
Вот. Если мы используем резонансный импульс, то вероятность обнаружить атом в возбужденном состоянии будет равна квадрату синуса от длительности импульса. Вот. Получается, что π пополам пульс в такой нотации нам как бы гарантированно перекинет атом из основного состояния в возбужденное.
Да.
Вот. А согласно вот этой картинке складывается такое ощущение, что у нас перекидывает из основного состояния в возбужденное не π пополам пульс, а π пульс.
Так, давайте вернемся. Пи-пульс – это вращение на блоховской сфере, значит, переворот стрелки фактически, да. Но вы про блоховскую сферу не хотите смотреть, вы хотите понять это сейчас по вот этой вот картинке, да? И вы сделали утверждение, что у вас амплитуда состояния пропорциональна квадрату косинуса, да? Или синуса, извините. Я правильно вас понял?
Ну, да. Квадрату синуса.
Ну, это же как бы, вот эта формула, она не содержит никакого вращения здесь. Это просто и состояние на сфере Блоха. Для того, чтобы описывать вращение, вам необходимо решить задачу Раби. То есть вы должны...
Нет, вот я...
Да.
Я как раз вот говорю, что если честно расписывать гамильтониан Раби и так далее, получится, что вот вероятность обнаружить атом в возбужденном состоянии равна квадрату синуса от длительности импульса. Вот. То есть там вот нету как бы одной второй. Вот, поэтому пиполам импульс как бы гарантированно перекинет атом из основного состояния в возбужденный. А согласно вот такой вот нотации со сферой Блоха, пиполам импульс перекинет атом из основного как бы в состояние 50/50.
Ну, смотрите, значит, мы же с вами говорим о гамильтониане Раби, его нужно написать, так? Все-таки это как бы, вот на слайде здесь ничего этого не было. Значит, дальше, чтобы решить задачу Раби, вам необходимо перейти в вращающую систему отсчета. То есть вам нужно перейти в координаты, которые вращаются с частотой внешнего поля. В задаче Раби получаете представление, эквивалентное блоховской сфере спин 1/2. То есть мы сейчас с вами говорим, в общем-то, о двух разных гамильтонианах. Одно дело, когда мы прикладываем переменное поле для двух состояний 0 и 1, а другое дело, когда мы уже в системе координат Раби, то есть в вращающей системе отсчета, рассматриваем ее как двухуровневую систему. Я думаю, что вот этот вот коэффициент, он там вылезет.
Окей.
Посмотрите описание вот задачи Раби и переход в rotating frame. Вот, и там это должно быть понятно. То есть там нужно пренебречь сразу медленно вращающимися членами, оставить только быстро вращающиеся, точнее, пренебречь, извините, быстро вращающимися членами. Вот. И дальше вот в этой новой reference frame получится значит, описание задачи Раби.
Окей.
Угу. Ладно, давайте я тоже немножко отключусь. Можно секунду.
Можно задать вопрос?
Да?
Вот я в бакалавриате учился не в РКЦ, на другой кафедре.
Угу.
А я бы хотел узнать, что именно вы проходили вот в курсе сверхпроводимости в бакалаврском. У меня тоже просто был этот курс, но я хотел бы узнать, насколько пересекается программа.
Значит, по сверхпроводимости мы проходили, в принципе, введение по книжке Шмидта в основном. Вот. Если вы хотите прочитать, это будет полезно. Но я сделаю введение здесь. Как бы полезно, конечно, вам знать, что такое сверхпроводник, как бы, и что такое эффект Джозефсона. Но я постараюсь все-таки, чтобы все остались на плаву, посвятить лекцию повторений. Объем моего курса – это книжка Шмидта.
То есть в основном был эффект Джозефсона стационарный, нестационарный и...
Ну, почему? Я рассказывал и БКШ, было 2 лекции, все теории БКШ, теории Гинзбург-Ландау.
Ага.
Рассказывал сверхпроводники первого-второго рода, и примерно там 3 лекции были про эффект Джозефсона и его приложение такой, ну, даже одна лекция про кубиты была введение такая. Но это все будет в этом курсе.
Ну, я был на другой кафедре, но у нас курс был вот ровно такой же. Есть...
Повторите, пожалуйста, вопрос.
Не, я говорю, что я был на другой кафедре, но у нас курс был вот ровно такой же.
Ну, тогда вам этого хватит. А вам читал Иван Храпач или кто-то?
Нет, нам читал Павловский Валерий.
Понятно. Ну, если вы это как бы уже слышали, я еще раз повторю какие-то ключевые понятия, и этого хватит нам.
Понятно, спасибо.
Конечно.
Я жду как раз этого лаба, мы как раз...
Так, ну давайте продолжим. Перейду к слайду, которым я остановился. Да, значит, я остановился вот на как бы основной идее, что мы приготавливаем начальное состояние, затем вычисление, это манипуляции, так сказать, вот этими квантовыми вентилями, либо однокубитными, либо двухкубитными. И, всегда это чаще всего бывает комбинация того и другого. И после этого измерение. Вот. Ну и как бы независимо от того, sorry, I switched to English, irrespectively of the type of the hardware which we use, this could be atoms, ions, or superconducting qubits, there are certain requirements. And those requirements actually were not obvious in the very beginning when people were suggesting to do it in theory. But then around the end of the last century, people have really needed to compare different platforms. And the accepted approach to compare different platforms, if they are good or bad or beneficial for quantum computing, is based on the so-called DiVincenzo criteria. DiVincenzo is a physicist, a mathematician and physicist who worked in IBM for many years and who is now working in Germany in the University of Aachen and Research Center in Jülich. And David DiVincenzo formulated about 25 years ago the criteria which are required for a functionable quantum computer. At that time, there were no quantum computer yet, but these criteria were very relevant to on the path to realize it. And first criterion, of course, is that we have a well-defined, extensible, or expandable qubit array. So array of qubits on which we could do one qubit gates and 2 qubit gates. Now, very important is that we need to prepare a certain state. And the most simplest state, of course, is the lowest energy state, which will be in conventional notation 000 state of all the qubits. The second criterion is to have a really long coherence time, because if we manipulate too slowly, if our gate is too slow, then the result will be meaningless because we have lost all the information on the way. So the gates must be much shorter than the coherence time. Besides that, we also need to have, of course, this universal set of operations, which means at least one 2 qubit gate and several single qubit gates. And also, very important is really to be able to measure the state of the computation, to be able to measure, if possible, simultaneously, the states of qubits in the array. So these are the five criteria which are relevant to compare different approaches. And some technologies satisfy them, some of them not satisfy them sufficiently. Actually, on the list of DiVincenzo criteria, there are two more. You see him, actually, this my picture from back 10 years ago when he was coming on my invitation to colloquium in Karlsruhe. He has two more, which is interconvert stationary and flying qubits, which means that we need not only store the information, but also transfer the quantum information over distance. And the seventh is transmit flying qubits from place to place. Well, transmitting and interconverting flying qubits is a technique which is used in quantum communication. But sooner or later, quantum computing will develop, and obviously quantum networks will be required, which means that one will need to couple quantum computers into a network. And if you couple classical computers into a network, then by adding two identical computers, you double the power of individual computer. If you connect quantum computers into network, you expand your Hilbert space. You basically increase the dimension of Hilbert space by many times equal to the number of qubits in the additional computer. And basically you multiply the power of computer. Therefore, until now, people were not really focusing that much on the 6 and 7 points of the Vincenzo criterion, but they're very important for the future. When quantum internet comes, then by implementing that, one should be able to multiply the power of quantum computers coupled into such a quantum network. That's very, very interesting. Okay, so let's talk about the coherence very briefly. There are two types of processes which are important for the coherence. First is that the qubit can change its state in a way that you go from high energy state to the low energy state. You go from state 1 into the state 0. And this process is called energy relaxation. In this case, you exchange energy with the environment, and you basically lose, with this energy, you lose the information. Another important type of decoherence is the dephasing. And this is basically losing the phase memory of the qubit. So once you have the state of the system into the block sphere, and then you prepare some state on the equatorial plane, then, for example, variation between the energy level separation between the levels will make the vector on the block sphere randomly diffuse along the equatorial plane, and this will be a process called dephasing. So this phase memory and the dephasing is limiting the manipulation. So the qubits must stay coherent. But besides the manipulation, we also need to do the measurements, and energy relaxation is the key thing for the measurement, because we must be sure that the states are not mixed when we want to measure the result, which means measure the projection, for example, on the z-axis. So both these times T1 and T2 are very important, and extending them is a battle which every platform for quantum computer has to follow. Now the hardware. So in this lecture course, we talk about the hardware for quantum computing, and as I promised you, I will talk later on today about trapped ions. Maybe also mention today or in the beginning of next lecture, neutral atoms. Then we briefly talk about the photons. I will not talk about spins in molecules, because this is not really scalable technology. Spins in molecules basically means that you can make a liquid of identical molecules, some diluted solution of molecules, and then study the properties of different spins, but you measure always the response of the ensemble of spins of many identical molecules. And the scalability here is limited by, let's say, maybe few tens of spins. You cannot really scale more. But the first quantum computers, actually, the first quantum computer which was made in IBM, on which Chuang made his factorization of number 15 into primes of 5 and 3 back in the year 2001. It was made actually using fluoroform, if I recall correctly, solution. So this was used for demonstrations, but not really for practical development. Now, all these systems are microscopic, and they naturally exist in nature. So one has to learn how to manipulate them. One has to find the ways to isolate them and manipulate them and read their states in a very controlled way. However, there are also synthetic quantum systems, or if you want, engineered quantum systems. And these are systems we can prepare in particular in solid or in condensed matter. And these are, for example, defect spins in crystals, like defects in the diamond, for example. These are spins in quantum dots. Here you see there is a surface of a semiconductor. There is a two-dimensional gas below, and these are the electrodes which are used to deplete the two-dimensional gas region under the electrode, and then form particular configuration of two-dimensional electron gas under the structure. There are also other systems more exotic, like electrons on superfluid helium. There are also magnons. There are also polarons suggested, and so forth, or excitons. All these systems, they have to pass the De Vincenzo criteria test before being really seriously considered. And some of them really did manage to do it until now, but still physicists think of different alternative ideas realizing. The most promising and productive approach nowadays, that's where many industrial companies rush to work using engineered qubits, are the superconducting qubits, which we focus in the major part of our course of this lecture. Okay, so I'm a bit slower today, so this is a summary of the first lecture. We talked about the introduction. I remind you spin 1/2 system, remind you the block sphere model to visualize the qubit states. We talked briefly about quantum gates and rotations on the Bloch sphere. We briefly discussed the decoherence, but we'll talk much more, of course, in application to different implementations of qubits in solid states. And really important is always to remember about those criteria, De Vincenzo criteria, which make it possible to realize a practical quantum computer. All right, let me stop sharing for a moment. I need to start the next series of slides. Any questions on the way? Comments, complaints?
All good.
Thank you. Any feedback is appreciated. All right. Okay, so this is the second set of slides where we're going to start talking about real physical systems on which quantum computers can be implemented. May I ask, have you heard any lecture on ions or atoms, qubits, some introduction or something? I'm not sure what was the first part of this course. You heard the quantum communication, or was it just theory in Fistech? The first half of the semester.
Actually, we have a year ago a course dedicated to studying different physical platforms. So we discussed it briefly, and we also have discussed what you previously mentioned, like De Vincenzo criteria. And
okay. Was it from Alex Fedorov or?
Yeah, it was from Alex Fedorov's group.
Good. So he's a great guy. He's a theorist. I have privilege or maybe a handicap of being experimentalist. Therefore, I think you have a different version from me, but some of things I think it's not bad to repeat after 1 year. Okay. So this is the slide you have just seen. And in this lecture, I have planned to tell you about trapped ions and neutral atoms. So we are going to briefly remember about electronic states of atom as a building block for nature. Atoms are very important, and something you learned in a general physics course. That's something you need to refresh here. And then we'll discuss about using ions as qubits, and then also continue with atoms, neutral atoms, not charged atoms as qubits. On the picture on the right, you see something which is often advertised, but I think it's not really a real thing. So these dots are ions, which are suspended in vacuum, somewhere here in this very little slit. And these ions are shining because of fluorescence, so they shine by illuminated by laser, and if they are in particular state, then they can make a transition to the fluorescent state, and then one can actually observe them with almost naked eyes. They're very small, but the wavelength of emission is of the order of micron, and having a light source of very small size makes it possible to see them under microscope. So there are two approaches, as you have seen. One can take an atom and either remove one or more electrons from an atom and get an ion. If you strip electron away, then you have charged particles, and they will interact via electric field, via Coulomb interaction, just as charges. So they will be easy to control by using electric fields. Neutral atoms are a bit more tricky because they have no charge, but they are polarizable. So in the very same Coulomb interaction will make it possible to make atoms interact, but now you will have interaction between electric dipoles. And there are states of atoms in which one can form so-called Rydberg states. These are the states of an atom which is excited in a very high state of the primary quantum number n. In this case, the atom is almost ionized and then gets really large in size of the scale of a few microns, up to a few microns. And then the dipole moment of that can be quite large, and it makes it possible to observe interaction between neutral atoms if they are trapped in small distance between them. So these approaches require high vacuum technique. So basically one needs to bring those few atoms in very high vacuum conditions in some chamber, which has very low residual pressure. And then one needs also to have these additional instruments, those fields, electromagnetic fields, which can hold ions at particular place and also hold atoms. Now let's remind very briefly the basics of an atom. So if you have electronic state of an atom, of course in the center we have the nuclei, which is having a certain number of protons, which means has a certain positive charge. And then the electron around states existing around near the nuclei forms a bound state, and its state can be described in this spheric symmetric potential, where you could basically represent the electronic wave function as a product of three parts. One is the radial part, which is characterized by the principal quantum number n. Then there is an orbital quantum number, quantum wave function p, and the magnetic quantum number ml. And this approach of describing the quantum state of an atom leads to three Schrödinger equations, which can then in terms give the eigenstates with three quantum numbers associated with the energy levels. So the state of atom can be then changed between 1 to 3. This is the primary quantum number. Then these SPD orbital states are different numbers of the orbital quantum number L, which can change between 0 and n minus 1. And then, as you know, the magnetic quantum number will change from minus L to plus L, and this is associated with the symmetry of the wave function of electron and atom. So basically, this is the standard assumptions of the atomic physics, and the example of the states which are actually characterized by particular energy levels, and transitions between them can be measured by using optical spectroscopy. So one can either absorb the photons by making transitions between the different energy levels, or emit photons. Now, to make these transitions, atoms have to be, of course, should have some allowed transitions, and one has to take into account selection rules, meaning that a photon is a particle with angular momentum 1, so it's integer, and therefore the orbital quantum number can change between 0, +1, or -1. Sorry, J number, excuse me. The orbital quantum number can be either changed to +1 or -1 due to this angular momentum of a photon. Then the spin number doesn't change because the photon doesn't carry spin. And this J is the total angular number in atomic physics, as you know, is sum of L and S. And S quantum number is the spin quantum number. It can be either -1/2 or +1/2. So some of these transitions are allowed, some of them are not allowed. If transition is not allowed, that means that actually if the state has no opportunity to decay, for example, the emission of the photon in the free space is prevented by modifying the environment, the emission of the environment. For example, you have some resonator which has a different frequency, and then your so-called cell protect from the emission of the atom, a particular frequency which is different from the frequency of the resonator. So in this case, the states will live long time. And of course, some transitions are forbidden, but they are forbidden in the first order. So there will be, of course, some factors which will lead to those transitions, but they will occur with much lower rate. And that means actually you could have enough time to do the quantum computation if you use those states as your quantum states to encode your states 0 and 1. Since atom is strongly anharmonic system, it's very often the case that you could choose very safely a pair of transitions, and then the frequency of transition between those two levels will be unique, which means that actually if you apply photons of this frequency, you will not excite any other transitions. In that respect, you could use any convenient pair of states as for encoding the information in fashion of two-level system. Of course, you need also to make sure that you are able to read out those states, and you might need to make sure that you can manipulate those states. And this is a matter of convenience. And actually, for a long time, the job of physicists was really to find convenient transitions in particular elements. There are many elements, and transitions have different features and different characters. Some of them are very long-living, some of them are very short-living. So basically, long-living transitions, stable states with long-living transitions form good qubit states, but you need other states to be able to read out those states. That's, of course, also part of the requirements according to the Vincenzo criteria. Now, one can manipulate atoms with light, and as you know, in the hydrogen, there are different lines, a series of lines. The Lyman series starts from deep UV, deep ultraviolet transitions. Then Balmer series already enters the optical range of visible transitions. This is transitions between states N2, N=2 and N=3. And there are also other series. Of course, most of them lie in the infrared range. So all those are optical frequencies with photons of the wavelengths of the order of a micron or less. And one can manipulate atoms with lasers. That's very convenient. On the other hand, there is also convenience of manipulating atoms by microwave frequencies. And this is in particular convenient because one can change the resonance frequency using microwaves. The resonance frequency is typically achieved either due to the spin interactions in an atom, for example, fine structure interaction or hyperfine structure interaction due to the interaction of electron spin with the nuclei, but also by applying magnetic field. And if you take, for example, degenerate state 2p, which have electrons with spin with different spins, then you'll have basically Zeeman splitting of this degenerate energy levels with states occupied by different spin states. And the transition lies in the range of some hundreds of megahertz or gigahertz, depending on the strength of magnetic field which you apply. So this can be either the fine structure type coupling due to the orbital coupling of the electron orbital motion to to the spin state, or the spin moment, or the externally applied magnetic field, as we all know. Now, how to use those transitions, we'll talk a bit later. Let's first talk about the choice of an atom. And one very particular atom, which is extremely convenient and very good for quantum technologies, is cesium. The reason is this is an atom which is standing in the periodic table next after xenon. Xenon has 54 nucleons. It's very stable. Nuclei also has all filled shells of electrons. And then by adding one extra electron there, one has the level structure, which is extremely simple and stable in time, and actually is not depending much on the external factors. And this cesium atom has been realized to be very convenient to make, for example, metrology standards. What happens there is that you basically add to xenon atom this 6s electron, and then due to the hyperfine splitting of this level, the nuclei of xenon has the spin 7 or 7/2 measured in Bohr magneton, and the electron spin basically interacts with the spin of nuclei, and this splitting leads to the frequency of about 9.2 gigahertz. And this frequency does not depend on anything in the world. It's just characteristic for this particular type of atom. And therefore, cesium atom has been used for metrology, and it's now being used for defining the standard of time. It's defined as second. Until 1967, the time was defined as a fraction with some crazy number in denominator. You see this crazy number, 31 million and some fractions of the tropic year for the year 1900, and particular day and so forth, because of course all these astronomical times are not really stable and only known from measurements. And after 1967, the standard of time is just a duration with this fraction of with this number of periods of radiation corresponding to transition between the two hyperfine levels of the ground state of the cesium 133 atom. So this is the standard, and actually the standards of time are now being used for GPS for all the modern metrology. This work on this direction are also work in Russia in FIAN, for example, in laboratory of Nikolai Kalachevsky. They've been working on these metrology problems with these and other types of atoms for a long time. So there are also other types of atoms which have certain advantages and disadvantages for these metrological purposes. So this is a very convenient type of atom, and this can be used actually to, do I have this here? Okay. This being used as a standard for quantum measurements already for a long time, but not for computing. Now, for computing, let us have this interesting slide. Have a look at this slide. I borrowed it from Gary Dell from a company called Quantum, which is a company dealing with atomic qubits. And this picture sort of summarize here technological approaches to quantum computing. And here you see that one corner is filled with superconducting circuits. We'll talk about them in length later in this course. Now, these are trapped ion qubits, which we are going to discuss here. And these little abbreviations here are the companies, startups, or bigger companies like Google or IBM for superconducting circuits, which already started their programs and started developing commercial devices. So for ions, these are Austrian quantum technologies founded by Rainer Blatt. These are IonQ, founded by Chris Monroe. And then Honeywell is the company which actually partially is a spin of IonQ, is already working already for a long time on this field. So it's really a platform which is having commercial approaches to use trapped ions for quantum computing. Here, for cold atoms, this era a bit younger. So there is a Q-era company founded by Michel Lukin and friends at Boston, around MIT and Harvard. Pasquale is a French company, which is founded by their competitors, but there are also other companies starting around the world. So these are called atoms qubits, which are not using charged atoms, but other neutral atoms. Then there are also photonic qubits, which we'll talk about briefly, and also some more exotic qubits, which actually relevance was debated for a long time. And I think Microsoft has now closed this program, at least to the knowledge I have. They're not continuing in that direction anymore. All right, so how can we use an ion as a quantum bit? Very simple idea. So first we need to learn how to trap an ion in the vacuum. So we need to find combination of electromagnetic fields to hold an atom, an ion, somewhere in free space. Second is to select, we need to select some long-living states and encode logical qubits, states 0 and 1, into those states. It has to have unique frequency separation. It has to have convenient frequency range for manipulation. Typically, this could be microwave or can be also laser. Then to manipulate, typically we also need a laser or microwaves to excite transitions. Then we also need to read out, and typically readout is done not by microwave but by optics, because one can observe the fluorescence of emission of light from atom when atom quickly goes from some high excited state to the ground state. But the readout works that one can basically apply a laser pulse from one of the qubit states into this short-living state, which has this optical transition with high emission light intensity. So basically, if we have two qubit states here below, 0 and 1, we manipulate them by either by microwave or by laser pulses. We need also to read out, and we read out for the state 1. If the measurement finds the qubit in the state 0, then basically with 100% probability, we'll go to this short-living readout state, and then a fluorescence from that state to this state, or maybe to some other state, will lead to emission of photons. So basically, once you have the pumping pulse on, the fluorescence can be observed by photon detector and a photon counter, and basically this will be result of the measurement the qubit was in the state 0. And then the probability of finding detecting different number of photons, of course, also depends on the resolution and noise in the detector. So this is an example of detector which has detecting efficiency of about 98%. So you detect some photons being emitted, and this will correspond to the state 1. But if there is no photons or only very few photons being emitted because of the noise and errors, this can be addressed to the state 0. Then by putting this combination line somewhere here between this black and gray bars, one can make an efficient detection efficiency. All right, so then next question is how to trap an ion. Well, naively, we just need some plates with electric fields. And if you take, for example, two capacitor plates with positive charge and put an ion in the middle, then ion will be sort of squeezed between the plates and cannot move up or down, but can always move to the side. Now, okay, so if we now fix the potential from the side, also put the plates, one can naively think that one can sort of localize ion in the middle. It doesn't work. And if you remember well your Sivuhin 3 part of the basic physics course, electricity and magnetism, there is the so-called Earnshaw theorem, that a static combination of electric, magnetic, and gravitational field, which means the conservative fields, is not capable of keeping an object in a stable equilibrium. So we cannot find a stable equilibrium under the action of just this well-known fields. And there is not much more one can use. Gravitational field is rather irrelevant. Okay, it's maybe relevant for metrology when you make an optical clock out of cesium atom. That's where they threw the atom up and down in the clock and then cancel for the gravitational line shift. But magnetic field and electric field, which is available to manipulate ions, will not make it possible to keep the ion in particular position. Well, so this is a kind of problem which is not completely unexpected, but which is not simple to handle. And it was this gentleman. Okay, so maybe I'll tell you first. I'll tell you first something else. So if you want to suspend some ion in free space, you need to make a levitation of an ion. There are different techniques of levitation. This is a bit kind of interlusion, which I have here as a slide. Okay, you certainly know famous Nobel laureate from physics, André Geim, my friend, who did, before he got his Nobel Prize, he actually did an experiment for which he got an Ig Nobel Prize together with Michael Berry, the very same Berry who invented Berry phases, mathematical Berry phases. So they had a paper together, which was titled "Of Flying Frogs and Levitrons." And this very paper got the Nobel Prize, and I think it was 2000. Yes, it was 2000. Now, if you want to levitate something, then of course there are different techniques available, but none of them can be applied to ions. But just to mention, these techniques could be, for example, levitating a diamagnetic object in free space, and this is levitating a frog, which was done by Geim back in Nijmegen a long time ago. And the idea here is that if you have a diamagnetic substance, and any material, any organic material is slightly diamagnetic, so magnetic dipoles, intrinsic magnetic dipoles of the material, they orient themselves against the magnetic field, and therefore this material is being expelled from the region of high magnetic field. And it means that actually the diamagnets, they move along the field gradient. And the experiment they have done, they were putting a frog in the gradient of field of a high field magnet. So the high field magnet means that there is high field in the core of a magnet, in the tube, where the field is concentrated by solenoid and is parallel to the axis of the solenoid. But once the solenoid stops, there is a large gradient, so the field actually expands in free space. And that's where you have a gradient facing upwards. And in the magnet, a diamagnetic object may have position of equilibrium. This really famous Friday experiment of André, where they managed to levitate a frog in the opening of a magnet. Of course, you need very large magnetic fields, roughly 30 Tesla or more, which is difficult to get and is only available in few places around the world. But this really led to something noticeable by physicists on the sense of, particularly on the sense of humor. It was quite amusing. On the other hand, these things also exist, and this was also the title of the paper, the joint paper, Levitron. That's a spinning magnet which rotates in non-uniform magnetic field. So actually, it doesn't violate Earnshaw theorem because the fields here are not stationary. The fields are non-stationary due to the rotation of the magnet. And that's something which actually can be bought also in the shop. So these Levitron toys are available. One can make a levitation, not mentioning superconductors, of course. That's why, you know, the levitation experiment is first thing you do to show the diamagnetism of superconductor. So it's available also. And this Levitron thing is actually similar to the ways one can levitate an ion. And this was proposed by this gentleman. His name is Paul. He got his Nobel Prize in 1989, just for the fact that he was able to trap ions in free space and then do interesting experiments with them. And the idea here was the following. So he designed the so-called Paul trap, it's named after him, but there are also other traps which can be realized. And the idea is not to use the stationary potential, to use non-stationary potentials. For example, if you imagine there are two rods like this, on one diagonal and then two rods on the other diagonal. And then you connect here some radio frequency source, for example, a frequency of few megahertz, such that you apply the same potential to the opposite rods. So for the moment when you apply negative potential for this is cross-section, negative potential for these rods, you apply positive potential for these rods. Then, of course, you can also play with the phase shift between the two potentials. Then in the next half period of the oscillations of this radio frequency source, there will be, instead of minus, will be plus here, then plus here, but then minus and minus there. And one can describe this potential as a saddle, and in the middle of the saddle, in this point, one can place a charged particle. And the charged particle will have the energy, which will depend on the coordinates in the two-dimensional plane perpendicular to the rods. It will look like this. So this two-dimensional plane, this is one axis, this is the other axis. Obviously, positively charged potential is here and there, and negatively charged is here and there. And then the particle is placed in a way that it's sitting on the position of the non-stable equilibrium. But the motion of the particle from that middle point has certain characteristic time. Depending on the steepness of the potential, it will start moving down, but will not really fall down immediately. It needs time to accelerate. But if you rotate the saddle while the particle is trying to fall down, then you can stabilize the particle in the middle. And then basically this is the idea of this power trap, that by applying the AC potentials along these rods, one can stabilize iron in a particular position in the cross-sectional plane perpendicular to the rods. And then one can apply also two potentials from the sides of the rods, and then close the particle in a potential well, a three-dimensional potential well. Of course, this trap is mass selective. It's tunable by frequency and amplitude of the voltage. And there are also some DC offset fields one can apply. So there is a whole field how to build those traps. But it works amazingly nicely. And that's an example of one of the pictures, maybe like 30 years ago, maybe even more, where you see here luminescence of four calcium atoms, ions, excuse me, separated by a distance of about 30 microns. And they are trapped, there are here four rods, and then two closing potentials from the left and right. So this technique actually allows making ion chains trapped in the in free space. And these chains can be very long. They can be of the length of the order of maybe up to 100. Now, typical spacing is on the order of a few microns. And this can be, of course, controlled by these closing voltages from the left and right. Now, the ions, of course, they are repelling each other. So they are repelling particles which are sort of pushed in the middle between two electrodes from the sides. And they can be accessed by laser beams from different sides to read out their states, to excite their transitions. And readout is very convenient because one can record the fluorescence just by measuring emitted photons with a CCD camera. So this is really very interesting scalable approach. One can make here are chains of ions of let's say a few tens or even up to 100. But how to couple the qubits? This was an interesting question, which was not trivial in the beginning. And then what was clear that ions can be excited in their mechanical motion due to their repulsive interaction between each other and repulsive interaction with the cup electrodes. Now, if you make one ion to move, then you can excite the motion of the whole chain. But the whole chain has, for example, in this picture, this example has 5 degrees of freedom. So it has 5 pendula, 5 balls. And if this pendula interact, one can think of different symmetry of the oscillations. Like, for example, there is this lowest energy mode, which is well, all pendula move either to the left or to the right. There is this mode where middle pendula doesn't move, but then others move in different directions. There is also this mode where the motion of the side pendula is opposite direction and so forth. So if one has 5 degrees of freedom, one diagonalizes the equation of motion, one gets 5 eigenmodes. Basically, the common mode is the lowest energy state because or the convenient mode because all the ions are taking part, and then there is no much difference between them since they all move together. So this is a vibrational motion of particles, and this can be also excited in the chain of ions. And then soon after the beginning of this work, I think pioneers in this field was the group of Rainer Blatt in Innsbruck in Austria. They were able to observe really the vibrational mode of strings of ions, and this is an example. The time goes horizontally, and this is the real coordinate, and then you see that there are this breathing mode of the chain of ions where the chain extends in the lateral direction, but there is also this common mode, as they call it Schwerpunktsbewegung, which means the center of mass motion. And this is the breathing Bewegung, breathing motion, Atmungsbewegung, the breathing mode. So these modes are possible. But then let's think how these modes are represented in the energy spectrum. And they are represented in the following. So if you move the ions in a particular mode, then the energy of the motion is added to the particular energy state of an ion. Suppose that you have now different ions and one of them is moving, the other one is not moving. Then you will have, of course, the slightly different energy states for those two ions. And when you have a motional state of an ion, then by adding more and more energy in particular mode, by adding phonons one by one into the mode, one can change the energy diagram of an ion from the left to the right, and then more to the right, and so forth. So here you have n phonons in the ion chain. Here you have n plus 1, and on the left you have n minus 1. And the states are slightly different in frequency because they are different by the frequency of this mechanical oscillation. So basically the energy between the difference between the corresponding, for example, lowest energy states of an ion are different simply by h bar omega divided by h bar omega, where omega is the frequency of particular mode. And you could put in this oscillatory mode, of course, any number of phonons you want. So you can change n from minus 1, from 0 to some large number. In fact, these modes are always excited because ions are never quiet. So you need to remove the energy from the ion chain to keep the ions not oscillating. And this can be done by the technique which is called sideband cooling. Basically, you use lasers to take the energy away from the ion chain. And by doing that, you can cool the chain of ions into the ground state. That's really, by itself, very challenging thing, but it can be easily done by using lasers. So consider that when you apply the transition, the frequency with a laser to excite your ion from ground state to the excited state. You go like in this middle. My mouse is frozen sometime. I don't know why. When you go from the lowest energy state to the highest energy state along this black arrow, you excite an ion from the ground state to the excited state. However, if you have a vibrational mode, then you need already to go to the next excited state to the state with one more photon, one more phonon in the chain. You need to apply this blue detuned laser, which means a bit higher energy. So by irradiating an ion with the blue sideband laser which is detuned in the blue side, you basically add extra phonon into the common mode. And by applying a laser which is red detuned on the red sideband, in opposite, you remove the phonon from the chain. So basically, you start from the middle here, and then you go with the red arrow to the left, and then by relaxing down to the ground state, by emitting a photon at the main transition, you will have an ion in a chain with one excitation of mechanical motion removed. And that's basically the technique which is used to cool down the chain of ions to the ground state. And then the same technique, the same approach is interestingly used by to entangle qubits by using this mechanical mode. So mechanical mode is often called a bus. It's being used to transfer the information from one ion to another. Suppose that we have now two ions, and we have two ions in the ground state. These ions can be arbitrary two ions of the chain. So it could be neighboring ions, could be also not necessarily neighboring ions, but they are both in the ground state. And then we prepare the motional state n with n phonons in the common mode. Now, once we are in the ground state, we first apply a pi/2 transition to the blue sideband of the first qubit, of the first ion. That means that since we have the qubit there sitting in the superposition with mechanical motion, we'll excite the transition from the state 0, 0, 0 to the state superposition of the state 0, 0, 0 and 1, 0, 1, which means like half excitation will be located in the ion, half excitation will be located in the motional mode. And then we apply pi/2 transition to the red sideband of the second ion, of the second qubit. And by doing this, we basically remove the excitation from this additional excitation from the mechanical degree of freedom, from the bus, from the mechanical motion. But we sort of complete the rotation of the qubit, now making the second qubit half rotating. In this case, we basically prepare the Bell state of the two qubits, 0, 0 plus 1, 1, making both qubits entangled. And moreover, since these qubits we choose by focusing the blue sideband laser on first qubit and focusing red sideband laser on the second qubit, we can entangle any desired pair qubit by using this technique. It's not limited to nearest neighbors. And that's a really beautiful approach that one can use. One can use in this chain. Okay, I don't have this picture here. One can use in the chain basically gates of any qubit with any other. So it's coupling all to all, which is very, very convenient. Now let's see what is the time doing. So how much time I still have? If I'm not mistaken, still like 15 minutes, right?
20 минут заканчивается.
20 minutes.
Сейчас 20.
Okay. So the technique to operate those chains is, of course, quite advanced. It doesn't include only this sideband cooling of the chain, but also the standard Doppler cooling technique, which is basically stopping the motion of an object by a laser field. You probably know this from optics. So when we apply a laser and the ion is not moving, then it sees the frequency omega. But when the laser is moving, sorry, the ion is moving towards the laser, then is the frequency which it sees is shifted upwards. If it's moving away from the laser, it's shifted upwards. It's conventional Doppler shift of the frequency. And then for Doppler cooling, people basically use, they find the Doppler limited emission profile, and then they use a laser line which is detuned, and then red detuned, which means the lower frequency laser. And the excites transition from the in the atom, but basically the photon which will be emitted over all with larger energy. It's in a way similar to what I discussed, but not limited to discrete levels, rather limited to, not limited to that, but rather than simply by gaining the energy of a moving particle by mechanical motion. So basically, by applying the laser at a rate detuned frequency, one slows down the laser, and this can reduce the effective temperature down to a few microkelvin, which means the motion of the velocity of an ion will be corresponding to the temperature characteristic temperature of only a microkelvin, and so forth. So there are also different limitations for that. Now, one use, of course, Doppler cooling in combination with some additional techniques, in particular also using the sideband cooling. And of course, Doppler cooling can be applied to individual ions, and this has to be done also repeatedly, because the ion will get exchanged with the environment and it will slowly warm up. So to be able to cool the system in the ground state, you need to repeat the cooling cycle correspondingly. And typically at the temperature which is achieved by Doppler cooling, there are still about 10 phonons left in the ion chain. So it's not really the ground state. You need to cool down below microkelvin. And vibrational ground state correspond to 0 phon. So really making this quantum computer work is actually very demanding and requires a lot of patience and tricks. And you may know that the team of Nikolai Kalachevsky succeeded at FIAN cooling down 2 ions to ground state and demonstrated 4-qubit quantum manipulation in Russia. Only, I think it was done last year. But in the West, this has been done already over more extensive time, as I mentioned, by group of Rainer Blatt and Chris Monroe. Now, sideband cooling technique is used actually routinely, and it's used after the Doppler cooling. And basically, it's done in the following way: that you simply apply a red detuned laser to excite the red sunband transition. And once you do it for all the ions, then all the energy of the system, all the energy of the mechanical motion, one by one, emitting the photons one by one, goes away, and the system is cooled to the ground state. And then one can also use the sideband cooling in combination with the manipulation. Of course, manipulation use the same technique of exchange of the energy, exchange of excitation with mechanical motion. Here, of course, one requires pretty efficient relaxation, and that means one can actually use the sideband cooling using a different transition than the transition which is required for the manipulation. And typically, the remaining 10 photons can be removed by the sideband cooling within time, which is limited by the relaxation of a chosen transition, but practical numbers are as short as 1 millisecond. So once you have done Doppler cooling, by doing the sideband cooling, you cool down the whole chain within less than a microsecond. And the technique is actually having limitations. So the final temperature of the Doppler cooling, so-called, is limited by the recoil. In German, it's called Rückstoß. And this is the remaining momentum after photon emission. So during the photon emission, of course, there is a conservation of momentum, and there will be a minimum energy which is left with the ion after emission of the very last photon, which has a limit of roughly 1.5 microkelvin. So this is a limitation of the Doppler cooling technique. Okay, so I think I gave you the idea of how to initiate, how to prepare the array of ions, how to read them out, of course, without going into details of particular transitions and particular sorts of ions, and also how to cool the chain to the ground state. Let us talk more with wider perspective. Is this approach feasible for scaling up? So, as I mentioned, by using these long chains, one can realize mechanical chains with, let's say, few tens or even hundreds of ions. However, the number of vibrational modes which exist in the chain increases greatly. And with increasing number of degrees of freedom in the chain, you have more and more different modes, and they start to cross and overlap, and the system, the frequency space becomes very quickly crowded. So, and also you need to cool down not only one mode, you need to cool down all those modes. So basically, to avoid mechanical motion, you need to cool down at many different frequencies. So really the task becomes very, very complex as the number of modes increases. The approach which people followed until now, this is the group of Monroe and the group of Blatt, was really to demonstrate algorithms with high fidelity, and they managed to demonstrate algorithms with very high fidelity and fidelity of the readout of 99% However, really doing the scalable approach where one would be able to have as many traps as possible and then entangle them, for example, by using the photons, has been less explored. But there is another approach which has been recently overtaken by industrial partner Honeywell. I will tell you a little more about that. Here you see a kind of a photographer view of the lab of Rainer Blatt in Innsbruck. This is Chris Monroe. Who actually both visited Russian Quantum Center many times and gave talks at the conferences in quantum technologies over the last 10 years. This player, which I mentioned, is the company Honeywell. Honeywell has been founded less than 10 years ago. And in the year 2021, last year, they reported a scalable approach to quantum computing. So they went along development of the so-called ion chips. So instead of using the three-dimensional rod structure, which of course is macroscopic and well established and so forth, they worked on the approach of microfabricate particular configuration with alternating electric fields using on-chip electrodes. And here you see the construction here. It's placed somewhere here in high vacuum. So this construction has a semiconductor chip, which has different metallic layers and gaps between them. And you see here that ions, they move from different locations, which are colored here by blue and yellow and orange and so forth. Now, the green lines are RF electrodes, which are shown to be 2 here. I think probably more than 2. There is also the ground oscillating field. I'm not sure, but they don't disclose this. And it's also not my field. But then these different colored spots are DC electrodes, which are used to manipulate ions in a very fine fashion. And they have chosen the approach where they use as a qubit combination of 2 ions. One ion, in particular a barium ion, 138, is used for cooling and is coupled to a nearby ytterbium ion, ytterbium 171. It has a transition at 12.6 gigahertz, rather convenient for manipulation. And then every erbium ion is always carried nearby barium ion. And then DC electrodes are always used to move those pair of ions around back and forth. They even learned how to swap the position of ytterbium and barium ions. So one is basically a refrigerator which cools down ytterbium nearly continuously, or kind of when the manipulation is interrupted. And then ytterbium contains the quantum information and is being used for storing quantum information and for reading it. And they used, for 2-qubit gates, they used barium, ytterbium, ytterbium, barium states, and also for manipulation, ytterbium, barium, barium, ytterbium states. I believe this is kind of coupled qubit, and this is probably the interaction switched off. All is controlled by high efficiency electronics with FPGA and use machine learning mechanisms or techniques, algorithms to learn manipulation of ions. Really very, very advanced technology. And by doing this manipulation, they were able to implement all the relevant steps. So they were able to store information, to apply gates, then apply gain gates, and then to read out the information and load the ions in a different register. So there is a very long paper, amazing paper published in Nature last year on that subject. So this illustration shows you single qubit gates and 2 qubit gates implemented between different pairs of ions. I still have slides today to tell you a little bit about atoms, but I would rather not mess around with that. It's only like 3 minutes left. Let me ask you if there are questions. So I'll stop today at this point, and we'll start with atoms next lecture. Let me ask you if there are questions. Was it too simple? Or you got tired after 2 lectures? Tell something, please.
Ну, много было понятно, и часть мы знали про охлаждение атомов, например.
Ну
и про ионные ловушки тоже.
Ну, я старался, чтобы было совсем просто, конечно, поскольку это не моя область, это скорее просто как бы такой рассказ беллетристический о том, как критерии Ди Винченцо выполняются на разных системах, чтобы вы могли сравнить и отчасти понять, в чем, собственно, преимущество масштабируемого подхода на сверхпроводниках.
Да не, хорошо вышло. Вот если касательно Мессиса просто, у нас еще куча других тоже курсов, и они почему-то очень сильно похожи, поэтому мы, наверное, вот в n раз все слышим. Ну вот, я думаю, они ближе к середине уже начнется что-то такое же. Конкретно каждому курсу свое. А пока все, все хорошо, понятно.
Ну хорошо, главное, чтобы
Спасибо
вы
вам.
не разбежались, не главное, но я надеюсь, что вы не все разбежитесь. Вот. То есть, конечно, сложность будет возрастать, и пока мы как бы говорили только о базовых вещах, которые вы уже слышали из других курсов, но дальше сейчас вот постепенно еще будет у нас такого обзорного вида следующая лекция. Ну и дальше уже вживую, я надеюсь, в Москве мы займемся сверхпроводниками. Напоминаю, что это будет 22 и 29 ноября. Я надеюсь быть живой в Москве и всех вас повидать в Скалтехе. Хорошо, тогда на этом давайте сегодня закончим. Спасибо всем за внимание. Вот. В следующей неделе. В следующий вторник.
Спасибо. Спасибо.
Вам спасибо.
Спасибо. До свидания.
Спасибо.
Можно вопрос задать?
Они делали в этой компании по 4 и каждую четверку считали, что это 4 кубита или...
Нет, такого не говорю. Просто не удержали.
Просто научились удерживать? Ну молодцы.
Да. Я тоже так считаю.
Нет, ну
Это
мутирует.
был первый эксперимент.
Ну, это да, самый первый.
Самый первый. Потом они учились больше утилизировать. А самый первый был 4
Ну, они много
иона
четверок.
кальция. Нет, самый первый это 4 иона было, ровно 4 иона
Да.
кальция.
А потом у него было масштабированность.
Ну, потом, да.
Ну, это много четверок.
Нет, почему не обязательно, что
Там может быть сколько хочешь.
там...
Да, они начали с малого, потом масштабировали.
Понятно. А там же...
Small steps.
Ну, там были
Повышается.
4...
Когда повышается количество, у них же очень теряется.
Ну, да. Вопрос в том, чтобы...
Я думал, там
Про это
просто у
не
него было несколько четверток, я подумал, что может просто у него это одна четверка, другая четверка, еще другая четверка. Каждая
Нет,
четверка
каждый четверки, это когда там были уже 2 атома, там 2 атома, помнишь? Интер и что еще? Вот
Да,
там...
что там за четверки? Ты понял, что это были?
Мне просто было стрёмно спрашивать, потому что я не очень внимательно слушал. Я такой, блин, наверное, все поняли.
Ты понимаешь, что за Итерби и Бари, вот это твердотельное?
Ну, я так понимаю, что это просто как дальнейшее развитие вот этих вот кубитных, ну, многокубитной системы, типа.
Нет,
Очень
там
много атомов.
просто дело в том, что если у тебя есть цепочка из разных атомов, ну, из разных ионов, типа разной массы, то там, типа, на них проще делать какие-то, ну, там, условно говоря, их проще запутать между друг другом, потому что у них разные массы.
Ну да. А с твердотельным-то как оно там? Ты понял вот про твердотельное, что он говорил? Как там твердотельность вообще прикрепительно?
Он что про это говорил? Я просто...
Кстати,
Я
пацаны нас
сразу-
записывают.
Один участник.
Но он не видит это.
Нет, один участник это мы.
Нет, мы-то один участник, но нас может кто-то потом послушать и такой,
Ну,
бля,
он
вот
конец уже
блоки.
говорил, когда Итерби и Бари. Или это...
Нет,
Или это там все еще получается?